Hello. In this video, I will be going over LeetCode 70, climbing stairs. So you are climbing a staircase. It takes n steps to reach the top. Each time, you can either climb 1 or 2 steps. In how many distinct ways can you climb to the top? Alright, so let's draw a picture of a staircase and hope that we have enlightenment. So this is the staircase, and we want to reach the top because, what's at the top? Because at the top, there's a can of Coke Zero, and I love Coke Zero. Actually staring at a Coke Zero next to my laptop for reference. And this is not the right brown. Very dark. Okay. And this is the Coke. Wow, that's a very dark brown. Okay. We want to reach the top stair, the nth stair, actually. And the key realization in this problem is that the number of ways to reach the nth stair is equal to the number of ways you can reach the n-1th stair, so let's call that A, added with the number of ways you can reach the n-2 stair, so B. So for any n, let's just call this relation f of n. We have f of n is number of ways to reach n, right? It's equal to f of n-1 plus f of n-2. That's mathematically restating the relation that I just kind of drew over here, right? So, I don't know if you recognize this, but this is actually the Fibonacci sequence. But let's assume that we didn't instantly recognize this. How would we kind of notice the pattern? So, starting from the bottom, at stair 2, and let's just call the base 0. How many ways are there to approach stair number 2? Well, there's 2. How many ways are there to approach 1? 1. How many ways to approach the base? 1, because you just start there, right? And we can also use the relation that f of 2, I'll just keep using red, f of 2 is equal to f of 1 plus f of 0. We know f of 2. That was kind of circular reasoning, but if you can just imagine, like, you either go from the base directly to 2 or from 1 below 2 to get to 2, you get what I'm saying, right? So that's how we get f of 0 is 1 for our purposes. And it's kind of like in the Fibonacci sequence anyways, when you're like, oh, you start with 1, 1, and then you go to 2, 3, right? So now we get to stair number 3. And using this recurrence relation, we get that there's 3 ways. And then for number 4, there's 5 ways. For number 5, oh my god, that's not a 5. Okay, for number 5, there's 8 ways because 3 plus 5 is 8. And then we see we have the exact Fibonacci sequence here. And the number of ways to reach the nth stair is just the nth Fibonacci number. Alright? This is the recurrence relation for a Fibonacci sequence. And in the Green Book, where I first read this question, the answer just states, yeah, it's the nth Fibonacci sequence. And unfortunately, there's no proper formula to find the nth Fibonacci number without just using, like, just brute force, climbing up the staircase of previous Fibonacci numbers to calculate whichever one you're looking for, right? So yeah, that is how you solve the staircase question. I think in the green book it's called like rabbit hopping up a staircase. It either hops up one or two at a time. So now let's look at the leak code, right? So you are climbing a staircase, it takes n steps to reach the top. Each time you can either climb one or two steps. In how many ways can you climb to the top, right? So one thing, if you read the discussion for this question, you'll find there's a lot of people complaining that there's a time limit error when you use the purely recursive solution. So let's just define the Fibonacci sequence. And use it on the test case, right? So here we see that the test cases are working fine, but you'll find if you go submit this for yourself, LeetCode's actually not going to accept this solution. And that's because there's so many recursive calls. The the time and space complexity is just low-key atrocious, right? If you visualize the recursive calls, you have you start from n and you go n minus 1, n minus 2. And then from n minus 1 you're going n minus 2, n minus 3, n minus 3, n minus 4. And you see where this is going, right? Like it's just holy, that's too many calls, right? But one thing you notice when you draw this tree is like you are repeating certain calculations, and that is assigned to use what's called memoization. Memoization, which is a dynamic programming technique where you kind of like save your work as you go. So you can reuse your previous calculations and not have to compute as much, but you're sacrificing or you're not sacrificing. Yeah, you're sacrificing space efficiency. You are um, bringing more space usage, right? So the way you would do this for this question is kind of just keep a dictionary of like n and the Fibonacci, the nth Fibonacci number, right? So, for example, we can already start with the base cases of, hold up, let me make this sorted. 0, the 0th Fibonacci number is 1. The first Fibonacci number is 1. Oh, sorry, no. The first Fibonacci number is 1. The second Fibonacci number is also 1. And you're using like 0 index. Yeah. So what I'm gonna do here is um, define the memo or dictionary outside of the function because you want to access it from any recursive call. So now you want to do if n is in memo, then you just return the nth Fibonacci number, and else you just add the nth Fibonacci number to this like dictionary, right? And now let's see if it still works. None and int. What's happening here? Definitely forgot proper solution. Memo and is between none type and int. Let me just print n. Let's see what's happening. 32101. Okay. So unsupported operand time score. Um, hmm. See if this works. Oh, okay. For some reason I thought it would just reach base case and then actually add. Wow, I'm mid. All right. Submit and yep, we get a good runtime, but as I mentioned, it uses a lot of space. So, yep. All right, that's climbing stairs.